Hello and welcome back to Crypto Engineering. We are now embarking on the part of the video lectures where we look into making cryptography, but really focused to the project that you will then be working on. So I will not be explaining all sorts of implementation strategies that kind of can apply to various ciphers. We will really just focus on implementing AES and what options you have. Now, the reason why we are doing this is because in the concrete project that you will be working on, you will be dealing with an AES implementation. It won't be just a plain AES implementation. It will be already written in a style to make certain attacks allegedly more difficult. So to be able to actually understand the code, I want you to talk you through just basically what options you have to implement AES. And I will be doing this by a really nice overview of implementation options that a while ago was made by a colleague of mine when I was still working in Bristol. And we have been using this slide set more or less in that way for a very long time because I think it really is the most concise overview of implementation strategies for AES. So if you at this point in time don't quite know what AES is, then perhaps it actually makes sense to pause the video here and first of all, perhaps if nothing else, read through the Wikipedia page so you get an idea what AES is sort of from a top level point of view. We did look at this in cryptography in the course that I teach in the summer term. You should have also seen something about AES if you did system security. So for those of you who have done these kind of things before, you should be all right. Now, we are not looking at the cryptographic strength of AES. We are really looking much more at the operations that define it and how you can implement those operations on different platforms. What options do you have? So AES is what we call a product cipher. That means that you have a number of functions that by themselves are actually quite weak cryptographically, but their combination already gives you a much better round function, and then by iterating the round function you actually get the cryptographic strength. So the individual components, they are not particularly strong, but they are efficiently implementable. This is why they were chosen in that particular way. So AES is important, right? I've not just picked a random algorithm for this course and for the project that you're doing. I've picked the block cipher that we currently have. It's the most widely used, most widely implemented algorithm that there is. So there's a good reason, in fact, why you should take some time to familiarize yourself with it. It's not something obscure that only academics look at. So it's so important because it replaced what was called the data encryption standard, or DES, that was kind of rescued for a long time by the triple DES variation that still is implemented in some systems. But really everyone should be using and is mainly using AES. There are different variations of AES that have been standardized with different key lengths. And there are minor differences when you implement AES for different key lengths, or more actually when you have to implement AES that it can cope with different key lengths. For many embedded systems, however, you would make an a priori choice which kind of variation you choose. And unless you need military grade kind of security, you'd probably go for AES 128. And so this is the variation that we will look at. This variation hence defines the size of the so-called state that AES operates on, both in terms of the actual state size and the key state size. So what we are talking about is AES 128. That means plain text size 1 to 8, ciphertext size 1 to 8, and key size 1 to 8 bits. That means the number of rounds is fixed to, and now it depends on how you like to count. Most people would say it's 10 rounds plus an additional key addition. Some people actually like to say from an implementation point of view, it's 11 rounds, whereby you have got two really special rounds. The first and the last one, the 0th and the 10th one, are different to the other rounds. So that's a little bit up to interpretation. And again, I hope you kind of took this away from either the cryptography course or perhaps from system security. AES in itself, it is a block cipher. It's a secure block cipher in the sense that there are no known attacks that enable you to recover a plain text given some ciphertexts. However, it in itself does not form a secure encryption scheme. So the moment when you apply any block cipher to more than one block, you need to think very carefully how you do that. So AES in itself is always either used in a what modern people call non-spaced encryption scheme, or you can also call it, it's used within a mode of operation. And many modes of operation are constructed in such a way that you actually never have to implement AES for decryption. The mode ensures that decryption happens although you only have AES encryption implemented, which is very cool and very sensible. So this is the reason why I will actually never bother talking about AES decryption. We will only focus on AES encryption in this video. So there is one thing to bear in mind, and I actually don't want to spend too much time on it, because from an implementer's point of view, although it's important to bear in mind, the implementation strategies that are out there and that you can use have in a way largely taken care of that little interesting fact. So you don't need to go deeply into it. And this is the fact that AES takes the bytes that it has in its state as elements of a very particular finite field. And it's the finite field with 256 elements, whereby the so now this is interesting for those of you who have a bit of maths backgrounds, because if you define finite fields and you have a non-prime, you have got a non-prime modulus, then well, how do you ensure that it's still a finite field? Because elements might not be invertible. If you've got a modulus, that's not a prime. So the way in which AES manages to get a 256 element finite field is by defining the finite field as a so-called extension over GF2, so the finite field with only 2 elements. And it has an extension defined by a irreducible polynomial, which is given here on the slide. So it's this kind of polynomial that AES utilizes for its modular reduction. Now, it could be really messy if you actually had to work explicitly with polynomials and do this kind of reduction. But luckily, in this kind of field extensions over GF2, most of the field operations boil down to XORs and ANDs. And so these are bitwise operations, and we will actually just leave it at that. You could do all sorts of nice maths, especially when it comes to the subbytes operation, but we don't really have to go there. But what is important to bear in mind that when we say, well, we are adding to a state byte and a key byte, or we are multiplying them, then we are not talking about multiplication over the reals or over the integers. We're in fact talking about multiplication, addition, subtraction, and division in this particular finite field that has got 256 elements. So to make this kind of more visible, so you kind of bear this in mind, Dan uses a very explicit notation here, which I think is very useful. So he kind of makes it sure that all the operations that you will see on the slides make it absolutely explicit in which kind of algebraic structure they live in. So whenever you see something with the subscript 2 to the 8, then you know this is this one very particular finite field that the AES designers have chosen. It's also kind of handy to denote finite field elements in a compact form. Often what we do for that, so this is not specific to this particular talk, is we use a subscript. So in the same way as here for the operations, we put kind of what is kind of our finite field size in the subscript. We can do that in all kinds of circumstances. So here, for instance, if you want to say, well, we are representing this in another finite field with now 16 elements, then for instance we can write this like this. So 0, 3 would mean that we set the 2 least significant bits in an array of however many elements, and everything here is represented via a base which has got at most 16 elements in its finite field. And so then this kind of array representation you can again change. You can write it in the representation that kind of refers back to, well, okay, so if this is a finite field with 16 elements, so how is this exactly defined? Well, it's defined again via a polynomial. This is again an extension field. It's 2 to the 4. And you could then also write it in a polynomial representation. So 1 and 1 here map to x plus 1. So that would be the polynomial representation. Again, luckily, we very, very rarely have to actually write this down, but it may help if you really wanted to backtrack absolutely precisely why certain things pan out the way they do, then this is kind of, it helps you for that. So AES has got this kind of concept of a state, which you can mathematically also understand as a matrix, right? So you've got rows and you've got columns. And you can interpret or you can index things via this matrix representation. So AES has got a number of round functions, and we'll now go through and reflect on how they work. So for each round, you need a round key, and this is given to you by the key schedule. We will only pay very, very cursory attention to the key schedule, because this is also not anything that we are really particularly interested in with regards to the project. So the key schedule spits out a round key for every round. So within the kth round, the way in which the round key is mixed together with the state is via the so-called round key addition. And this is an addition in the finite field with 256 elements. And because this is a binary extension field, it essentially means that this addition in the larger field is equivalent to the addition in the lower field, so it simply is XOR. Yeah. So you've got here the state, which is always denoted by S in its sort of matrix notation. Here you've got the state that corresponds to the key. Yeah, and then if you add the correct state bytes together, then you see this is sort of addition in this binary extension field, and the addition here really boils down to XOR. Then the next round function is the nonlinear substitution box. It's the application of that. There's only one, so all the state bytes get fed into the same substitution box. So this is simply then applied to each state byte individually, as you can see here from the notation on the slides. So that's kind of easy peasy. Then you have got shift rows, which means you are shifting elements within a row. And if you sort of look carefully at the index here, then you see that the first row, this remains unshifted. So the index by which it is shifted is 0. If you look at the second row, then you see S10 moves actually one position. So it's kind of a wraparound by one position. If you look, then the next row is a wraparound by 2 positions, and the final row is a wraparound by 3 positions. So also in a way, not very taxing. And then maybe the most complex one is mixed columns. So here we take the state column-wise, and then we do a multiplication with some specific elements, and multiplication has to be understood in that finite field f2 to the 8. The way in which these kind of coefficients here have been derived has something to do with coding theory. And again, this goes completely beyond the course. This is about block cipher design. If you really want to inquire why these are nice numbers. So we will not go there either. But what we will have to think about is how do we realize a multiplication by 2 in the finite field that has 2 to the 256 elements. And so we'll need to think a little bit about that. So as I said, there is also the key generation algorithm, the round key generation. And this, in fact, also just uses the standard round function. So there is the S-box, sub-bytes is used. You use exclusive ORs, so the addition mod 2 to the 8. And then there are also certain round constants which have to be added in. But all in all, it's not very interesting. So when you put these things together, then you can construct the AES encryption function. As I said, there are, depending on how you want to see things, it's either 10 or 11 rounds. Some people consider this bit here as a sort of initial round, where only a key addition takes place but no other round functions. Then you've got 9 of the so-called full rounds, where you always do a sub bytes followed by shift rows, followed by mixed columns, followed by add round key. And then you do a final round where mixed columns is missing. So AES was designed to satisfy a range of needs. It was meant to be a versatile block cipher. It was not meant to be specialized to a very, very specific application. So the first thing was that it had to work well on resource-constrained platforms, which is a fancy word for a smart card or for an embedded device with a small 8-bit microprocessor. So this is also motivating why state elements in AES are always 8-bit elements, right? This is a handy kind of word size for an 8-bit processor. So what you do then, if you have got such a small device, is, well, you just use the AES representation as it is natively, because it's perfect for that. And you can now decide whether there are certain things that you want to pre-compute, which means that you're spending memory of your device, or whether you want to do everything on the fly. So things you could pre-compute, for instance, is the sub bytes function. You could compute this and store it as a table, and this is what many implementations will do. But obviously you're trading a bit of memory for some computation time. The other things that you could do is, if you know that in your application the keys will remain fairly static, you could say, well, the key schedule, I might well implement a function for it, but actually for as long as I'm not exchanging a new kind of key for communication, I will run my secret key through the key schedule, and then actually I store all the resulting session keys, such that when I actually do an encryption, I'm not doing the key schedule on the fly, I just have pre-computed round keys available. So again, you're treating then memory for speed. So here is now sort of a kind of pseudocode that represents an implementation strategy of AES for resource-constrained platforms. So important to sort of see here is that in the pseudocode, there is the idea that you have somewhere data structure which represents unsigned 8-bit integers. So if you do an add round key and you have got your data represented in that way, then really all what you do is XOR with the right kind of elements. Sub bytes, you would then perhaps assume that you have a pre-computed S-box, so all what you do is a table lookup. So that's fairly easy. For shift rows, you can do this efficiently with minimal sort of additional variables. For the first row, you don't need to do anything anyway because the shift offset is 0. For the second row, you need one extra variable, one temporary variable to kind of store the first element that gets sort of shifted out and copied into the final row, and then the rest you just do by direct copying of elements. For the second row, you need 2 dummy variables. For the third row, you need 3 dummy variables. And for mixed columns, you need to have a little bit more thinking, because there you need to do this multiplication of some of the input elements with a constant, either 1 or 2 or 3. So with 1, you obviously don't need to do anything. But if you multiply a specific element by 2 or by 3, then remember this is a multiplication over a very specific algebraic structure. So it's not just normal multiplication. We need to work a little bit harder for that. And so what you do here is you essentially have to write a function that multiplies by a constant. And because the constants that are small, that are used in mixed columns, it makes sense to implement a function that essentially realizes a multiplication by 2, because that means that with this function that does a multiplication by 2, you also get easily a multiplication by 3. Or you do a multiplication by 2 and then you add the element again, which gives you a multiplication by 3. So a lot of people will then implement this kind of multiplication by 2 function, which in the AES specification is actually called xtime. And then, well, you just do the right multiplications and then you just XOR the right elements together, and this gives you your mixed columns. So when you then have your overall AES structure, you have got an initial round which only consists of a round key operation. You have got your kind of standard round which does sub bytes, shift rows, mixed columns, And then at round key again, whereby the round key, you might generate it on the fly. And then the round 3, which is the final one, is the same as you're just not doing mixed columns. So this is missing here, mixed columns. So the key schedule here on the left-hand side of the slide is also pretty straightforward. It's not really a major focus of our implementation and your exercises either, so I will just leave that. And here on the right-hand side, you then have essentially got your AES encryption function simply put together. So you've got, you write the result in an array of 8-bit integers, which is your ciphertext. You take in a similar size for the message, you take in a similar size for the key. The round keys are again specified in the same manner. And so you then sort of put things together. You've got your initial round, which is just at round key. You've got your standard round, which you do 9 times. And then you've got your final round, which is missing out, simply mixed columns. And then you just copy the resulting state into the ciphertext and you're finished. So that's the sort of implementation strategy for a resource-constrained device. One thing that we need in here, which we haven't really talked about, is this X-time operation. And that means you multiply a field element essentially by a constant, which is 2, or if you represent it in polynomial representation, it's also called X. This is why you call it X-time. There are 2 options for that. Well, so this is a multiplication over a finite field with 256 elements. You might as well pre-compute it if you have got enough storage on your resource-constrained device, or you have to do it on the fly. So on the fly is not massively difficult, right? All what you want to do is a multiplication by 2. You're doing this with elements that live in a binary extension field. So they are all things which are represented by 0s and 1s. So it's an array of 0s and 1s. And if you want to multiply binary numbers by 2, then all what you do is a left shift. So this is really quite handy. So your multiplication by 2 over this specific finite field is then, well, you do a left shift. And then obviously you have to see whether you've generated an overflow, whether your element is already larger than 255. So if it's 256, you need to do the modular wraparound, which you would do via subtracting the modulus, which is a polynomial. That polynomial can be represented as a binary string in this particular way. So if you now look at the X-time operation that is kind of encapsulated here in its simplest way, what we do is we check, is the leftmost bit 1? If so, we are expecting an overflow, which means that we do our left shift and we XOR it with our irreducible polynomial. And if it's not 1, then we just do a left shift and we don't bother with anything else. So it's fairly simple. The problem with this left-hand code is that you can see there's a conditional branch. And in one part of the branch, you're doing more things than in the other part of the branch, which means that you're generating timing differences. And one of the things that you will learn to pay attention to then in the third part of this, of the taught part of this course, is that any kind of data-dependent differences are normally cause for concern, because they leak information about the internal state and they can be exploited by adversaries. That leads to side channel attacks. So this here is functionally correct on the left-hand side. This here is okay, functionally correct, but not very good because it's not timing constant. An alternative way of computing this in a completely constant fashion is here given on the right-hand side. So what you do is you essentially shift out the leftmost bit into a variable called t. So this may be 1 or 0, depending on what the number is. If it's 1, then you know you need a modular reduction. If it's 0, you don't need it. Now, what we'll do is we essentially now take the rest of the variable x, and we are doing a right shift for 7 positions, which means that the topmost bit, if it's 0, then we then x is just equal to 0. And if the leftmost bit was 1, so the topmost bit was 1, then this right shift means that x is equal to 1. So we have now essentially found our topmost bit that we have that we would have lost here by the left shift by the multiplication by 2. We found it here. If it's 1, so if x equals to 1, then multiplying 1 by this term here, which is in fact the representation of our irreducible polynomial, means that we get our irreducible polynomial. If the leftmost bit had been 0, then x here at this point is 0. So either at this point, either x, if the value that we had originally had the topmost bit set equal to 1, in this case x represents our irreducible polynomial, in which case the final step here means we are doing our reduction, or it had been 0 all along, in which case this multiplication will have also produced 0, which means that the XOR here does not perform modular reduction. So this is a functionally equivalent piece of code to the left-hand side. So it will do a modular reduction when it's necessary, but you don't need, you don't produce any timing leak. So really the right-hand side is what you will want to see in an implementation. Now the other component that we need is the sub-bytes operation. As I said, one way of doing that would be to just pre-compute it. In fact, if you look at the AES specification, sub-bytes is in fact there's a table there provided, so you don't need to make the effort, you just encode the table. But in fact, the table has come from a composition of two functions, f and g, whereby g is an inversion. So g is actually A inverse in that specific finite field. And then f is a linear function, a linear mapping that is applied to g. And that linear mapping is given here as this kind of matrix, multiplication plus an addition of a vector. So as I said, there are now a few options. You pre-compute the whole thing, or you compute part of the box, S-box online, and part of it may be already offline. This really depends on the implementation, I would say, constraints. And I would say that although you've got a composition of two functions, f and g, either people pre-compute the whole lot or they don't. To compute f, you can actually write out this matrix multiplication, which Dan has done here very kindly. And that looks, as he says, not very nice. But if you actually try and code it, it's not that terrible after all. And for the inversion itself, there again, you would have a few options. Some of it are only theoretical options because implementing a brute force search is really a bit daft. The other option you could do is implementing the extended Euclidean algorithm for inversion. You can also use Fermat-Seidel theorem. That also tells you how to compute an inversion. And you can do that also over smaller fields. So there are a number of variations. But what most people do is they will actually use Fermat-Seidel theorem as a starting point, because what it tells you is that your inverse is an exponentiation of A, and you can actually work out what is the most efficient way of doing this exponentiation a priori, because Q, which gives you the field size, is of course fixed for AES. So it's 256. So Q minus 2 is 254, and you can work out what's called the optimal addition chain to compute this inversion here. So this is the optimal combination of additions and multiplications. Here is the pseudocode to do just that. The inverse here is given then as this kind of addition chain. That actually is not the optimal one, but never mind. It's at least one that is working. So this is an implementation that you would do for a resource constrained device. What would you do if you had a device that has lots of memory, for instance, and a wider data bus? So for instance, it's not an 8-bit processor, but a 32-bit processor. Now the 8-bit state is still not a bad thing, because you've got the 8-bit state, but you've got a 4x4 matrix. 4 times 8 is 32. So it's a kind of natural mapping to a larger word size on a processor and a larger bus size. So what then people do is they pack basically either rows or columns in one data word and manipulate that. Other things are really equivalent. So there are choices about pre-computation and so on. What people notice is that the main bottleneck when you implement things is mixed columns. But what you can do is you can play a little bit around with the representation and actually write out mixed columns as a sequence of field multiplications and additions. So this is what has happened here. This is mixed columns simply written out with the matrix with the constants that we've seen before, now worked out and already multiplied in. And then you can start grouping operations in a specific way, which then enables you to essentially take some of these individual elements and actually notice that, well, they are always the same, which means that you can actually pre-compute them. If you've got lots of space, you could actually pre-compute these tables and store them in memory. And this is what's called then the T-table approach to implementing AES. So essentially you compute what is the operation. Sorry, I go once more back. So here what you see is that we take all the elements that are indexed with 0. Here you take all the elements that are indexed with 1. And so because of how we've grouped them, we can then pre-compute this kind of overall operation for all the input elements that you can imagine. And with that, you then get these 4 tables, T0 to T3. You pre-compute those, and then mixed columns essentially is a combination of table lookups and XORs. And yes, you spend a lot of space on tables, but this makes mixed columns really very efficient. And it gets even better because what goes into mixed columns is in fact something where subbytes has happened before. Subbytes in fact is also a table lookup. And it's also 8 bits. So in fact, you can merge the subbytes table into the T0 table, which means you don't have to store any subbytes table anymore. And essentially your table lookup for mixed columns takes into account the entire round. So your encryption round basically becomes a number of table lookups. So this really is quite nice. So round 2 then, so this middle round, which does subbytes, shift rows, mixed columns, and then afterwards at round key, just looks like that. So you've got essentially a number of table lookups which get XORed together. And that is that. Very, very neat. The key schedule, you can also do interesting things, but as I said, this is not our focus, so I will always skip over the key schedule. So your overall encryption then looks as follows. You still have got your initial round 1. You've got round 2, which in fact you can loop unroll, so there's no reason to write a for loop in fact, and you can just write down what the input columns are, and then you've got your final round 3, and that's all in fact extremely neat when you write it down, but it costs you memory. And then strategy 3 is a mix of strategy 1 and strategy 2, and that makes sense if you've got a processor with a larger word size and bus size, but it's in an embedded device, which is really often the case. So a very important and well-liked processor family is with an architecture from a company called ARM. So the ARM Cortex series is in loads and loads of embedded devices, and they are exactly 32-bit processors, so 32-bit words and 32-bit buses, but it's resource constrained. So now you want to have a little bit of a mix and match, which means you would probably do this packing of 8-bit variables into a 32-bit word, but probably you wouldn't go down the T-tables route because you don't have enough memory. So you might just do the round functions again on the fly. So this here now reads perhaps a little bit more compact. So you would do your X times, you would try and do that on all the 4 bytes that you have packed within one word simultaneously. So you now have to mask out the topmost bits, the most significant bits of all of the 8-bit words. You still do a left shift with the whole shebang to the left. You still isolate your topmost bit with a 7-bit shift to the right. You still kind of mask then the leftmost bit if it's 1, and you multiply with the irreducible polynomial, then you still sort of get your reduction polynomial there, and then you still do the same XOR as in the fmul or xtime operation for a single 8-bit data word. So it really is the same thing by and large, but you replicate it in parallel on the entire word. And then mixed columns, you write like this. So this is similar to before. It's just you ensure that you've got a more efficient xtime operation in use. There is a little bit more explanation of why this works so well. I don't think that's massively important for us. So this is if you have to implement AES from scratch, which you won't have to do. And here again, we have done an overview of kind of some of the round functions, SBox and so on. They would be the same because there's no real value in kind of replicating the subbytes lookup over the entire word. In fact, there you get the data word over the bus, and then you have to mask out the individual components, and then you have to go through and do the SBox lookup. Okay, so we've got the same operations here. That brings us to the end. So it's actually quite cool perhaps to once really go through these implementation options that there are, because it is actually, I would say, quite remarkable how well AES lends itself for both really small devices, so 8-bit words and 8-bit kind of ALU really, and then also the same, it also lends itself really well for kind of 32-bit architectures, and you can make a lot of trade-offs in between. So even for kind of devices that already have a 32-bit architecture but are still kind of memory constrained, you can still find a good sort of trade-off. And so it's one of the reasons why AES is perhaps a popular algorithm, not just because it's been standardized, but because it does work fairly well across a large variety of platforms. It's not the most efficient for every single situation. So AES has been standardized now many, many years ago. There are more modern ciphers out there which perhaps do a better job in very, very specific applications. But AES is really a very, very good working horse in a way across many different scenarios. I hope that running through these implementation options will help you to work out what's going on in the AES implementation that you are looking at in your hands-on part. And thereby this particular video tutorial comes to an end.